Good morning, myself Neha Jagwani and I am research scholar at Department of ECE, BMS College of Engineering, Bangalore. My paper ID is 140 and my topic is a survey on detecting location based faults in wireless sensor networks using machine learning and deep learning techniques. This paper presents the survey of machine learning, deep learning and time series methods used to detect anomalies, data-centric faults and system-centric faults in wireless sensor networks. Starting with a little introduction to wireless sensor networks. Wireless sensor networks are a set of autonomous, tiny, low-powered devices that can sense, process and communicate among themselves within the network and send the data to the base station. Their function is to continuously monitor the environment where permanent presence of human is not possible. As we know, the sensor nodes are densely located in adverse environments and left unattended for a long time, and they are generally deployed once in their lifetime. So it is very important to make the system error-free. Thus, the concept of fault tolerance is very important in wireless sensor networks. There are various types of faults in wireless sensor networks that are classified on the basis of behavior, time, components and location. Behavior based faults are divided into hard fault and soft fault. Hard faults are the faults due to which the node stopped working, but in the case of soft faults, sensor nodes can continue to work but sense, process and transmit faulty data. Time-based faults are divided into four types: permanent, intermittent, temporary and potential. Temporary faults are the faults that occur because of environmental conditions such as temperature, humidity, vibrations, etc. These types of faults usually occurs once and then disappears. Intermittent faults that do not occur continuously, they appear and vanishes repeatedly. Next is permanent fault. These faults include built-in effects and burn out of electronic components. These faults remain in the network until the faulty components are totally removed. Next is potential faults. Potential faults occurs due to depletion of hardware resources and which are responsible to reduce the network lifespan. Third is component based faults. As the name shows, if the fault is on node level, it is node level fault. If it is on link level or sync level, it is on communication link faults or sync level faults. Then the next is location based faults. Location based faults are of two types: data centric faults and system centric faults. System centric faults are due to calibration issue, battery failure, hardware failure, communication failure, low memory, environment out of range and etc. Whereas data centric faults are of following types: offset faults, it is due to the when a displacement value is added to the actual sense data. Next is gain fault, when rate of sense data is different from the expected rate. And then stuck at fault, when the variation in sense data series is 0. Then out of bound faults, when the observed values are out of bounds of expected value. Then the spike at fault, when the output contains high amplitude values at constant periods. And then is data loss fault, when there are some missing data during the specific time interval. Thus, machine learning and deep learning has come up with the solution of the problems in wireless sensor networks. As we know, machine learning is a subset of artificial intelligence which automatically learns and improves from the study or experience and works without being explicitly programmed. Many applications have found remarkable use of machine learning, which increases accuracy, reliability, performance and speed of the devices. This paper is done to find the role of ML and DL in detecting anomalies, data-centric faults and system-centric faults. So starting with the role of machine learning and deep learning in anomaly detection. First of all, we should know what is anomaly. Anomalies are any unexpected events or observations that can occur due to any fault or deviation in data. They are diagnosed as any deviation from the rest of the data patterns. So this table shows us the role of machine learning and deep learning in detecting anomalies in wireless sensor networks. Reference number 16 has compared LSTM and RNN, that is long short term memory and recurrent neural network, to find the anomaly in the data, and found that LSTM is more robust than RNN. Next, the reference number 17 has compared bidirectional neural network, principal component analysis, forward neural network and recurrent neural network, and found that BRNN perform best. HB and then reference number 18 has compared three models based on three different concepts, that is HBOS, MCD and IF, and found that the domain based anomaly detection, that is isolation forest, works best in case of time series data. And the reference number 19, that in that the detection procedure is divided into two parts. First, the classification algorithms are used to detect the anomalies in the data, and then the regression algorithms are used to find which attribute exactly crossed the threshold. It is found that random forest perform best for classification job and additive regression perform best for the regression job. This table represents the use of machine learning and deep learning in detecting data-centric faults in wireless sensor networks. In reference number 5, authors have compared 6 different algorithms and found that random forest performed best among all the algorithms. In this paper, the faults have been induced in the dataset at various fault rates like 10%, 20%, 30%, 40% and 50%. In reference number 20 and 6, authors have used support vector machine to classify these faults. In reference number 20, SVM is trained by different kernel functions. The efficiency of classifier has been increased by increasing the training data and the number of features, but this created overfitting. To overcome this issue of overfitting, cross-validation technique is used. In reference number 6, the using the kernel function, SVM algorithm shows good capacity for nonlinear classification. Reference number 12 and 14 have used extra tree classifier, which is an ensemble method technique, to detect these faults. In 12, a context-aware fault diagnostic scheme has been proposed. This scheme utilizes extra tree classifier, and it uses two ML classifier. First is based on multi-level classification, in which the faults are classified on the basis of context, and then the data is trained by ET to find out the causes of each fault. Then this output of first ET classifier is given to second ET as an additional feature which detects the sensor faults such as hard, drift, etc. In reference number 21, an improved NN architecture known as threadful long short-term memory neural network has been proposed to find out the faults in the wireless sensor networks. In reference number 22, a new nature-inspired algorithm is used, that is improved fault detection crow search algorithm, and it has been compared with already existing algorithm and found that it performed best than RF, KNN and DT. In reference number 23, 4 enhanced ML classifiers has been used, that is enhanced KNN, enhanced extreme learning machine, enhanced support vector machine, and enhanced recurrent extreme learning machine. These classifiers are compared and found that ERELM perform best among those. This table represents the role of machine learning and deep learning in detecting system-centric faults in wireless sensor networks. The paper 24 focuses on failure of communication links in wireless sensor networks, as decisions can be affected due to problems in communication link even if all the nodes are functioning correctly. Paper number 25 focuses on calibration issue and low battery issue. Paper number 26, 27 and 28 have used time series algorithms, ARIMA, ARMA, MA and AR, and these techniques provide great reduction in power consumption in wireless sensor networks. As in 28, an automatic ARIMA based data aggregation scheme has been developed. This battery saving scheme eliminates the inherent redundancy of raw data in wireless sensor networks. This is done by decreasing the number of transmitted values between sensor nodes and aggregators by using time series prediction model. This is the conclusion of our paper. Wireless sensor networks has been considered as promising technology that can perform the function of sensing, processing and communicating to attend numerous remote sensing applications. The sensor nodes consist of a large number of hardware and software units. There are various issues and challenges in WSN which can hinder the functionality of sensor nodes and network. We have given a detailed classification of various types of faults that can occur in WSN. This paper focuses on location-based faults, which is categorized into data-centric and system-centric faults. One of the most effective way to detect these faults is the use of machine learning algorithm. Thus, in this paper, we have surveyed on the use of machine learning and deep learning algorithms for detecting anomalies and location-based faults in WSN. We have summarized these ML-based algorithms in a tabular form. It is also concluded that the techniques like random forest, support vector machine and neural networks has proved better than other algorithms. Many researchers have used modified and advanced versions of already existing algorithms for detecting faults in WSN. Still, the problems in WSN are not fully resolved and need attention from a research community. Also, there is less research in models dealing with multivariate time series data. Thus, there is a scope of using some new, more advanced and modified ML and DL techniques to detect multiple faults in WSN such that sensor networks can be used more effectively in variety of applications. These are the references used in the paper. Thank you.